Okay, this is on section 9.7. A couple of you guys asked some questions about this. So let's go over this again. Last section in the book. So this is dealing with circles, obviously. So let's put a few out here. Now, everything to this date, this part of the text, has been dealing with angles. So what we've been doing all up to this point, just to put everything in perspective here, is, look, we talked about a central angle, and if we did this, that we would create a central angle here, and the measure of this is the measure of this external arc. Then we said, well, what if we put the point out here on the circle? That's called an inscribed angle, and this angle here is 1/2 this inscribed arc. And then we moved various angles outside where we had and I'm just changing color inks here, where we had the vertex moved outside, where we could have two, let's say, tangents, or we could have, this tangent and the secant, and finding out this measure of this angle by virtue of subtracting from this larger this smaller and dividing by 2. So now this section, however, is dealing with not the measure of angles, but the measure of the lengths of the segments inside. So similarly, rather than having a vertex angle here or an angle right at the center of the circle, we could simply draw two chords and intersect them like this, so that it's obvious that this is not the center of the circle whatsoever. So if we label this A, B, C, and D, and we made this point P, this is a little bit similar to how it's presented in the book. What this theorem says is, look, that the length of section AP times the length of, I'm sorry, this should be, one of these needs to be D. So we'll just make this AD. We'll say that AP times PD is equal to BP times the length CP, which is kind of cool. So regardless of where this point is within this circle, it makes no difference where we are, that if we put a point here, anywhere inside here, we make this point here, we draw a line through here and through here, and we have this point. These two segments are going to be equal to each other. Now, very similar to what we did earlier with moving this point of reference outside, we can also, with another circle here, we can also say, well, what if this vertex, these vertices here, are outside? So the simplest one is theorem 912. So we say, well, okay, let's move this out here. So let's say that we had a point completely outside of the circle, and we wanted to make lines to the circle using this. So this particular theorem says, let's not have two tangents, let's have two secants. So let's draw these two secants, just like that. So now this theorem, which is theorem 912, says that, look, it's relative to these lengths here, and I'm going to use a similar notation here. This is P, B, A, and this is D and C, and this is D and C. This says, look, and I'm going to use math language here, the length of these two segments are a function of the external part and an external part. So it's internal and external. So I'm generally reading it here when we have two secant segments drawn from an external point, the product of one secant segment and its external segment equals the product of the other secant segment versus the other one. In other words, if this is entirely R and this is entirely T, then RS, and this is the other one here, this is point S, and this is point U. What they're saying is that the entire one, R times the external, is equal to T times the external. Okay?